Nico. This talk is aimed to non-cryptographers and non-mathematicians. As a web developer, I find CK really interesting, but also really challenging. So I wanted to give like a brief walk through the KZG and how it works. We're gonna go for why KZG in Ethereum right now, how does it work, what we implemented, what we developed, and some challenges and conclusions. So the KZG is needed for EIP 4484, that it's also known as proto-dank sharding. And why is that? Why we need a KZG in Ethereum is basically because we want to reduce gas costs. Remember the rollups take transactions and from time to time publish these transactions on the mainnet, right? So we have the mainnet, and there are also like chains that from time to time will be putting their states, their data, their transactions, etc. on the mainnet. There could be many layer 2s pointing to Ethereum mainnet, and all these layer 2s will publish their state on layer 1. The thing is that if we get cheaper L1 data, we could get cheaper L2 transactions. The problem right now with data in Ethereum is that we need to have the whole blockchain data in order to check the validity of the blocks. What does this mean? We need to have all the data from block 1 to hash it, and then have all the data from block 2 to hash it, etc., 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 right? The Merkle proofs need all data to be available to check for validity. That's the problem. The solution right now are polynomial commitments. So polynomial commitments only need to evaluate a polynomial on a specific point to check for validity. How does this work? So imagine we put like all the blockchain data, we plot it and put it on a graph, right? This is hyper simplified, but imagine we do this. And then we create a polynomial that passes through all the data points, okay? So this new polynomial will be easier to storage. And when a new user comes by and says, hey, I have this point x1, we can check that if the point is inside the polynomial, and if it is, it's gonna work. If the point is outside of the polynomial, it's not gonna evaluate correctly and it's gonna fail. So far, that sounds easy. The problem is what happens if there is a malicious user that is trying to cheat us. So could be the same exactly point, but the user doesn't know the polynomial, right? So imagine that this malicious user is trying to make the lighter polynomial valid, right? So in this case, this should fail as well. This is where trusted setups comes into play. So trusted setups are kind of like random points that we generate in order to check for the polynomial and the user points, right? So in this case, the user will input the point and also a bunch of random points generated by the trusted setups in order to validate the polynomial, and that will validate correctly. And this way, we cannot, the malicious users cannot cheat the chain. If all the data, in this case, all data does not need to be on the node, so we can make some kind of storage ephemeral, right? They call that the storage. And if we make it ephemeral, then we can make a cheap L1 data. That means that we can make cheap L2 transactions, and we reach our goal. So the KZG is a polynomial commitment scheme where you can prove that your data point passes through a specific polynomial. In simplifying some things, you need the polynomial, you need your point, and you need random points generated previously, right? These random points need to be encrypted, because if they are not, the system can be cheated. And this is where the ceremony, the trusted setup comes into play. The trusted setup, what it does is it generates a structured reference string, so the random points. The idea is that to compute these SRS, we need a sequential computation, multi-party computation. So we need a sequencer that takes the line and keeps all the computations in a sequential order. Each party generates a secret and adds it to the SRS, and the way they add it doesn't break the SRS, and at the same time keeps the result encrypted. So for example, imagine the SRS is G to the power of 12. I add my secret that is 7. My secret is 7, so I multiply it by G to the power 7, and I get G to the power of 19. At the end of the day, the G to the power of 19 is the public data. It's just like a random huge number, right? But my contribution is inside, and if I forget the 7th, the system will be secure. To decrypt all the values, to decrypt the real value, we will need all the parties to collide to show their secrets. Right now, the KZG ceremony on Ethereum had like 140,000 contributions. So I think that's the probability of that happening is really low. So as long as one participant forgets his secret, the chain is secure. What did we implement here? So we did a bunch of things. So first we did a browse-based computation, client computation. That was the official site where you could like join in and compute. Jeff helped us out a lot in this. We also had some like CLIs. So if you didn't trust the browser, you could like run your own Rust client or your own C client and compute the ceremony. There were also another things like community browse clients that were developed. So there was a really nice cat game that you will move the cat, and the movement of the cat will generate the entropy of it. And also we needed a core part that was the sequencer. The sequencer was this server, this coordinator that was in charge of keeping the sequence of participants, right? The challenges and conclusions that we have on implementing this were, so first, the sequential coordination. So we had a server that had to keep the order of every participant's contributions. And the first problem that arrived here was what queues should we use? So we could have used a FIFO structure, that a first come, first serve thing. So like if everyone in the room will like to contribute to this, they will have to be in line, and we will go one by one. The line will be really long. And in case of this ceremony, the people on the line will have to keep the browser open, and that will generate a mess. And the other alternative, the other strategy we had was to build a lobby. A lobby was a pool, so you will enter into the browser, you will say, hey, I have time to contribute. You will be on this pool of participants, and the sequencer will randomly select you to participate. This way, if your browser will lose connection by any situation, you could come back again, and in theory, you will have the same probabilities of participating in time. Another great challenge that we have is that, so for EIP 4484, the trusted setup was really fast, circuits were not high, but right now, as we were hearing about with Jeff before, we have the perpetual powers of Tau that take like 40 hours to compute. They are like 100 gigabytes size files. So that cannot be handled on the browser. So that's an interesting challenge to work on. And the last challenge is spam. So how do we prevent bots from participating on these ceremonies? And at the end of the day, preventing other like real participants from going in and contributing on time and all that. one solution that we took was to use third-party login services. So you could, on the KZG ceremony in Ethereum, you could log in with GitHub. But at the end of the day, how do we trust that GitHub is giving us like real users, are validating that they are real users? And another mechanism that we used was that addresses needed at least n transactions to participate. At the beginning, I think there were like 6 transactions requirement to participate, and later, no wait, I think it was 32, and then we keep lowering down until like everyone could participate. But at the end of the day, if I am new to Ethereum and I don't have transactions on the mainnet, I could have not participated on KZG ceremony. So I don't know how fair is that. That's it. I'm open for questions. If you need more information, I'm happy to help. Yeah.
First, some applause to Nico. Thanks, Nico. Yes, we do have time for questions.
Thank you very much. Actually, I also checked the ceremony, and I'm wondering, if you want to share more details about the danksharding, and let's say, I see there is a change from the initial design till now. So if you have time to talk more, we can share later.
That's a really good question that I don't have the answer to right now. So I was only part of building the trusted setup thing. I am not really like into the details of how a proto-dank sharding will be working. From what I know, it's gonna be released on the next release on, I think it's Cancun. Yeah, but no, I don't know anything more, sorry.
Hi, thank you for the talk. And let's say hypothetically, I would like to do my own ceremony for KZG. Do you have any suggestion or advice for me?
Oh, cool. Yeah. So on the PSE team, some of our team members built Potion. It's a super interesting tool to run ceremonies. So you could like search the repo. We could talk later. I can share you the link. And it will help you to run the coordinator and also like run CLAT and everything, so you can like run your ceremony smoothly. Thank you.
Thank you.
Any other ones? Some applause to Nico. Thanks so much.
Thank you very much.